Great, this is the Universal Image Embedding 4th place winner's call. This is Maggie from Kaggle. I'll turn it over to you, Andre, for introductions.
All right, hi everyone. Thanks for making time to discuss with us the solution today. Congratulations again on the great performance and the great system you built. That was really impressive. I know you already gave a presentation in the workshop too, so thanks for being able to meet with us once again, where we'll probably be able to discuss a little bit more in detail. So yeah, to introduce myself, I'm Andre. I work in Google Research in the computer vision team. So maybe I'll hand it over to other people in our team, maybe Kaifeng next.
Hello, everyone. My name is Kevin. I'm working with the features team inside Google. So we are also developing the features for the Google products. Yeah, I'm really excited to hear about your presentation, and that's my part. Mario?
Yeah, so hello, everyone. Hi, I'm Mario. I work in Google Lens, and I was working on preparing the evaluation sets for the challenge. And yeah, I'm also like very looking forward to the presentation and discussion and things that we learned today. And maybe Uri can also introduce himself.
Yes, hello, I'm Uri, and I work also in Lens with Mario.
Great, so maybe we can hand it over to Marcos and Simon for introductions briefly.
Yeah, sure. So yeah, this is Marcos Conde. I'm a PhD candidate in Germany in computer vision, and I'm also Grandmaster and data scientist at H2O AI. And yeah, I'm a Kaggle Grandmaster, so I'm used to kind of the environment. So yeah.
And hello, so my name is Simon, and I'm located in Paris, and that's fun to see that everyone is located in a different place. I'm working now as a freelance data scientist, and my expertise is in computer vision, and I'm working a lot in medical imaging too.
Great, so Maggie, should we move on to the presentation?
Yeah, you can go ahead and start presenting your slides.
Great.
Okay, so I will share my screen up, and hopefully it will work. Okay. Okay. Okay, let's go. So first of all the credit of this presentation goes to Marcos, who presented it at ECCV a few weeks ago. So I'm just repeating. So I don't know if some of you were there already.
Andre was there because he was the co-organizer of the workshop, and I think Kaifeng was also at least, I don't know if virtually or in person, but yeah, for sure.
Okay, so you already know the talk.
Okay.
So the voice will be just a bit different. So the agenda, like very straightforward. We speak just briefly about CLIP, our solutions, and the results. So first of all, I would like to mention that Ivan is not here. So Ivan, he is a programmer at Salesforce, and I think he did a big part of the job for this competition.
Yeah.
He's in Australia, and I think there is no time schedule that worked for him for both the US, Europe, and Australia. So introduction, the goal of the competition was to design a feature extractor for image similarity search. And there were two specificities for this challenge. The first one is that we had to design a feature extractors that work for any kind of images, whether it's a landmark, photography of a product, or an artwork. And the second one is that we had to create a very compact representation with only 64 dimensions, even if 64 dimensions is a lot, in fact. And so the search criteria was simply Euclidean distance. As I think all the competitors, we used Vision Transformer pre-trained using CLIP, which stands for Contrastive Language Image Pre-training. So I guess you already all know what is CLIP. And for me, I guess the two very interesting stuff about CLIP. First is that it's pre-trained to maximize the cosine distance between image representation and text representation, which is exactly the same as minimizing Euclidean distance, which is the objective of the challenge. And the second one is the scale of the data set that were used. For instance, the VIT huge model is pre-trained on a data set with 2 billion images. And so if you have a frame rate of 10 images per second, it will take 6 years just to see the data set. And so I think it's like hard to grasp how big these data sets are. And so CLIP models were very interesting because they were the first to get good results in zero shot on ImageNet. And I think that they have been surpassed by other models which are not open sourced. And there are some of these models at Google, like including Align, Basic, or Coca. And so I would be curious to know if it works better for you guys. And why is this models are amazing is that they have to align both the image and the text. So two different modalities, and something that everyone is sure it would work, like using multimodality would work. I think that's one of the first examples to make it real. So my contribution to this challenge personally was to design a zero-shot baseline. So I was interested to know how far you can go without using any data, because I'm a bit lazy. So the idea, the problem with the different CLIP models is that the embedding dimension is too high for the challenge. So basically for VIT huge, it's 1024. And so the question is, how do you reduce the dimension to 64? So I first tried just to randomly picking some 64 neurons, which already get quite decent performance. So that shows how amazing these models are. And the next step for me was to design a simple dimensionality reduction technique. So I picked PCA because PCA, even if it's not the optimal solution, it preserves most of the variance, so most of the distances between points. But instead of collecting a data set of images and perform the PCA in the space of images, I created the PCA in the text space. And this for two reasons. First, because it's very easy to generate a text data set with categories which are very similar to the ones that could be in the test data set. So I just ask GPT-3 to generate a list of words, of dishes, of artworks, of products, etc. And the second reason why I think it was interesting is that I think it's much easier to cover a big distribution of concepts with words than with images, because the word cat, like, it covers a lot of images of cats. And so with this simple solution, we achieve a top 5% score on the challenge. And I published a notebook on this. But it was not enough to get to the top 5. And I will let the hand to Marcos to explain how we fine-tune the different models to get a much better performance.
Yeah, okay. So I don't think I can ask for control on the slide. So yeah, I will just tell you, Simon, when to.
Next slide, and I will.
Yeah. So the point is that the initial solution is completely, zero shot, in the sense that we don't train the model. We just play with the interesting properties of CLIP, of the image and text alignment. And in order to achieve the most competitive performance and aim to win the challenge, we needed to fine-tune the models towards the distribution that you indicated in the web page, right? Because at the end, Lion has 2 billion images, but you specified already quite an accurate distribution of the percentage of landmarks that might appear in the dataset, the percentage of artwork, at those things. So we need to fine-tune the model and use a similar distribution. So the details about the datasets that we used and everything are in the paper and in the GitHub. I don't remember exactly now the name of the datasets, but were public and enumerated in some Kaggle post. The main points is that basically we use some common tricks from image retrieval. We use an arc face head that probably you saw on the Google Landmark challenges from previous years. So we borrowed that technique from other approaches. And in order to fine-tune, you can check the code, because we implement many tricks from the papers that we cite here from Bortzmann et al. About robust fine-tuning of zero-shot models, meaning layer-wise learning rate decay and custom augmentations and those sort of things. Because in our case, we train for very few epochs, 1 or 2 epochs. Most of the models 1 epoch actually, because after the second epoch, the weights get destroyed. The original pre-trained models, pre-trained weights get destroyed, and we lose performance. So yeah, that is quite tricky. And I saw that there were other competitors that trained longer, and I assume that it's because they used other sort of tricks and they tried harder than us. So can you move to the next slide? Yeah, so this is just to visualize more or less what the distribution shift could look like, in the sense that the Lion, I don't even remember. I checked the website, but I don't even remember the distribution and the amount of images that they cover. But we really need to adapt the model from that general distribution to the new distribution. Move to the next one if you can. Okay. I thought that there was another one in the middle, but anyway, the point is that there were a couple of tricks like model soups from Wartzman, and it's explained in the paper the idea of averaging the weights from the zero-shot model and the fine-tune model. The idea is that the zero-shot model has these general properties and can generalize to out of the distribution samples, right? And the fine-tune model adapts to the new distribution, but loses kind of that general performance. And we want to leverage both models, because at the end it's the same backbone and it's just 2 different sets of weights, right? So these guys from Machine Learning Foundations, I think they published a paper at ICLR this year or last year explaining model soups. And basically what they propose is to average the weights of the zero-shot model and the different fine-tuned versions. There are, I think, 2 papers. One paper is model soups, and another paper is WISE FT that goes in the same direction. And you have the references in our paper, anyways. And the idea is that you can see more or less our evolution, like the baseline zero-shot model. What happens when we fine-tune and we average the weights from the zero-shot model and the fine-tune one doing a model soup. The performance keeps improving, and in order to be as competitive as possible, we just ensemble 2 different encoders. And in terms of time, actually, I think so the VATL was very fast, and the VATH was relatively fast, and we later discovered that we could have included a 3rd model. Actually, some guys used the 3-model ensemble, so there is kind of room to process those 100,000 images under 9 hours using another backbone, and probably boost the performance to maybe a bit more, maybe 0.7. That could be possible, I think. And I think the rest of the details are in the paper or in our code, but obviously we will answer now your questions.
Cool, thanks. Do you have more slides, or should we start asking questions now? Okay, cool. Yeah, just wanted to confirm that this was the right point to ask questions. So maybe I can start with one. So you're doing the kind of two sorts of, in a way, ensembling. Like the model soup itself is some sort of assembly. So it seems like you do the model soup for each model, and then you also do ensembling, as the table was mentioning.
Yeah.
By
So
these
the model soup would be like a self-ensemble in the sense that it's per backbone. And then the kind of the classical ensemble would be joining two different backbones. Yeah. That at the same time, the weights of both two different models, those weights are the result of averaging the weights from different different fine-tuned version. It's similar to SWA. I don't remember what it stands for, but it's this weight averaging, stochastic weight averaging that you have in PyTorch, where basically you can average the weights of different epochs in order to improve training convergence and consistency. I think it's very similar.
Right. So go ahead.
And also, you can't average the weights of CLIP-L and H because they are not the same models. But yeah, I read the same. It's also like SAM, if you know the optimizer. Like you search for a flatter minima and you average different models in the low loss area, and you get a flatter minima. For me, that's amazing that it works. This is such a simple idea.
Yeah. So then, if you can go back a few slides, I just wanted to ask a question about this ensembling. The previous one.
This one.
This one, yeah. So the VIT encoder is the one that you do the soup, right? So the neck is kind of separate, I guess. You don't do a soup of the necks, is that right?
I think everything.
Yes.
There you catch me, because that is something that Ivan did. But I assume it's everything, including the neck.
Yeah. Yes.
I see.
Like you average all the weights.
Got it. I guess not for PCA or even for PCA.
No, not for PCA. That's for sure.
I imagine. Yeah.
So maybe in the final submission you actually didn't use the model soup, only like the two different backbones that were concatenated, whose output.
No. So the point is that those two different backbones that we used, the weights of each backbone are the result of averaging and doing the model soup for each backbone separately.
So each backbone was model soup, and then also you concatenated two different.
Yeah, exactly. Yeah, it's like a two-level ensemble, let's say.
So you actually have to run like 4 different models, or. Like
yeah. So it's the zero shot, and then we fine-tuned each backbone at least a couple of times, and I don't remember the number of experiments, but more or less in that direction.
So I had a question. Actually, in the ensembling, there was a sum. Was it sum in the embedding or concatenating? Actually,
probably is the concatenation. Yeah.
Yeah, this one here. Oh, I was gonna ask about that. Okay, cool. Thanks for clarifying.
I have one question about the PCA part on the text. I think in the archive paper you showed that running PCA on text works better on when you use PCA on images, and I think there's like 1 to 2% difference. I think that's quite interesting. Yeah, I guess it's pretty new among all the participants. I think you explained that because the text sort of covers more concepts and images in a sense.
That is our theory, because actually Simon spent a whole afternoon trying to generating embeddings for different data sets and then trying to test it. And every time we tested it, it didn't work with images. And I think it's just a matter of variability. With text, you can create arguably whatever amount of text descriptions you want and huge variability. But with images, you are limited to the images themselves. So
yeah. So in the end, so how do you come up? I guess you use the GPT to generate a text, right?
Yes. And it would have been good to have a chat GPT, because now you can directly copy paste the list.
I see. Okay, got it. And
because I had to manually create the list because it didn't work at every attempt, etc. I just try to respect the distribution of which was on the description of the web page.
I see. Got it. So you basically follow the distribution of the
Yes.
images, and then
Yes.
you create this list.
But
I
how
see.
many like items are there in this list? I just like generate like a million size data set. Of,
No. It's just 3,000.
I see.
So it took me maybe 1 hour to create this small data set.
And have you checked the length of the text, or does it matter in the result?
Yeah, so I tried like to do kind of prompt engineering, but basically just putting the raw word, or I think I added a picture of, and I get a slightly better performance. But prompt engineering is not super interesting, so I didn't spend that much time fine-tuning the best prompts.
Yeah, that part is quite interesting. Thanks for the explanation.
Yeah,
actually, there was a paper about finding the best prompts for these sort of models. Yeah.
I think it's this year's NeurIPS. It's learnable this prompts.
So if I may have some additional questions about this. So you mentioned like 3,000. Those were the prompts or the output text?
Like, the number of words.
Yeah, that were. And so I think in the paper you mentioned that for the image PCA you used 10,000 images. So I was wondering like how did you select this data set of images that you first you basically first used PCA trained on images and then you compared it to this PCA on text. And like I was wondering how you selected those 10,000 images for.
It was so someone on Kaggle posted like a tiny data set with that kind of distribution that I pointed out and that you described, and is annoying some Kaggle post. I think is I think it should be like a footnote in the paper. I think.
I think okay. I think I have it.
So we basically sampled images from that data set.
Which is supposed to be representative of the distribution.
I see. So I guess maybe, I don't know. Did you try also larger, or there is some maybe problem with computing the PCA for larger sets? But
basically, I didn't see any progress. Like for instance, doubling the number of words from 3,000 to even 7,000. I don't know what's happening here. It didn't change the performance, and same for images. I don't see a big improvement by just doubling the size.
Yeah. So probably
I'm really wondering. Like the only theory I have is like language is better to describe a high-level concept than images. I don't find any other reason. Maybe we didn't use the right data set. So if you get the answer, I'm super interested.
And
so for I'm sorry, Mario, finish first.
Yeah. And did you use this text PCA also? So you also used PCA in your final architecture, or also in the others? And what was the text PCA or some image PCA?
No, so it was the PCA on the embeddings produced by the fine-tuned models.
Oh yeah, so it was of course it was different
embedding,
different embedding space.
Yes.
So you had to use some data set to also find the PCA, right?
I'll need to leave now. Just me. But thank you so much, and it was really interesting to see your solution.
Yeah. So actually, I have to leave in 5 minutes. Something happened. So I mean, Simon can answer whatever question, and my email is in that. But the point is that if you require something from me, just feel free to ask me now.
Yeah, I had a question about the arc phase, because you guys are doing arc phase on the 512 dimension, but then actually using PCA to get the 64 one. So why not do arc phase directly on 64? And
that's a great question. That is actually what most competitors did. Basically, it didn't work. I think is the point that it's quite tricky to keep like the VIT backbone weights, train that part properly is already tricky. Fine tune it, and then ArcFace has some hyperparameters like the number of subcenters and those sort of things. Maybe we ran 2-3 experiments, we didn't get the right hyperparameters from the beginning, and we thought, okay, this is not a good direction, but maybe giving another try, it worked. It could have worked. And I know that other top solutions did that, learning directly the compressed representation. Intuitively, I would say that that is the best option, because on PCA we actually did some experiments, and you really lose a lot in those in order to compress to those 64 dimensions. I don't remember what was kind of the average variance, but you lose a lot of information. So probably learning, tackling this problem as a learned compression in that direction would be definitely the best possible solution.
Also, I've got plenty of questions for you. So when you're done, I would like to know if I can ask some of it.
Yes, so maybe let's exhaust our side's questions first. Kaifeng, did you have one, or?
I think Mario asked my question, but I have another one. So I guess when I look at the solution, I think you only use 2 data sets, right? It's the landmark and the product 10K.
Yes.
And how were them selected during the training? And have you tried other data sets? And is the reason that you don't use them?
So about other data sets, the problem is that so it's quite, in the sense that we as Kagglers, we are a bit lazy. So if someone posts a good data set out there, we just use it. Collecting the images, scrap the images from the internet, all these things were like having to think, is this data set something that we can use? Is the license good? Can we use it, etc.? We just go to the list of data sets posted there, and we just use them. So I remember, because for the experiments that I run were only on the data, only in that dataset, but I remember that Ivan tested different datasets, even ObjectNet internally, just to see the performance. And the problem is that even if you increase the number of samples, like the number of images in general raw, the performance doesn't really improve, because it's a matter of the quality of the images and how well represented is the distribution. So I think it's tricky to find a proper data set. I remember that the first place solution explained that they leverage it more data sets. I don't think that actually makes the difference, because if you think our model is quite similar, kind of the single model is quite similar and trained with way less data, and the performance decay is meaningless in the sense that 0.01 or something like that. So I don't think that more data is, and obviously another reason is that more data implies more training time, and we don't have infinite GPUs or training time.
So when you're training, how did you just merge the landmark and product 10K?
Yes. So it should be. I think there is a notebook in GitHub for the pre-processing of the data, but basically we sampled some images from Google Landmark from the Your Challenge dataset. I think the Google Landmark 2020, the clean version. We just sampled some images and we just merged with the product dataset. I think that was the merge. And the point is that since landmarks and artwork are already like 30% of the distribution, roughly, or 35, is already like if you do well on those kind of distributions, you can perform well overall on kind of considering the challenge. One second, I need to charge my laptop.
So I had a question on the kind of the training. So I think you mentioned you use some tricks like kind of different learning rate decay depending on the layer and stuff like that. I saw some teams kind of use like like fine-tuning the backbone, but only with a very small learning rate, such that it wouldn't change that much, while the the neck and the head would have much larger learning rate. Is this the kind of approach you use too? I mean, I guess you fine-tuned a little bit the backbone in order to do the model soup later too, right? Just wanted to.
So for Marcus, the question was about the importance of the decay of the learning rate, and whether we the learning was that different between the neck and the backbone. Well, I don't have the experience to answer this question, but from what we exchanged with Ivan, this decay on the backbone was very important, and that's also something I saw from different feedbacks on Twitter from Ross Whiteman, saying, "Oh, it helped a lot for fine tuning." And for my own experience, also of trying to fine tune with the whole model, you have to take a learning rate of 1 minus 6, so it's very, 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 very low. So I don't know if you have your own experience, Marcus, but I would say
so I remember that basically we borrowed some techniques, many techniques from machine learning foundations from OpenClip, and most of those tricks that you can see in our code are borrowed from the paper that is there cited, robust fine-tuning of zero-shot models. Those guys really perform all the empirical analysis, and they have very, very clean code, and obviously they know better than us all the tricks. So yeah, I think I don't remember exactly the numbers, but I think we wrote some the most important information at the paper. But the idea is that the neck has a certain learning rate, and then the more you move, if the neck is here, when you move to the first layers, you decay it more. So the neck has a kind of the highest learning rate, and then you keep decaying it. But yeah, I don't remember now the details. The code should be quite clear.
Sounds good. I think on my side, I don't have. Maybe one quick question is like, how many GPUs did you guys use? Just out of curiosity, like.
So I think we had so it depends, because originally we had one 3090 and 3 3090s distributed between us. But for the last week, in order to speed up and get a nice boost and try to win, I rented two. It was 1A100 really, but it was just a couple of days just to test some experiments. So.
Right. Yeah. Thanks.
I have some open questions. So, is there anything that you expect it or them to work, but it didn't work at all during your training, let's say?
Sorry, what?
The question is there anything or are there any tricks that you expect them to work, but in the end they didn't work at all?
Yeah, well, so for example, the learned compression of the 64-dimensional embedding directly, that is quite tricky, I think. And actually, that is, in my opinion, what made the difference for the first solution, the first place solution, because the rest is quite a standard, is the same kind of approach. Then I would say I was surprised with, but I'm sure. So I was surprised, but now I'm not, in the sense that I thought that training, longer would help, especially if done properly with these techniques, with this learning rate decay and everything. The point is that after the first epoch, the performance decayed. So also it's quite tricky, to compare models, because each team has a different internal validation, right? So maybe in my data set that we selected for validating, it was bad, but maybe if I test it on another data set, I could see, like a good performance increase and change everything. I think that is key. I would say, like, for as my last words, because I have to go to another appointment, but for future challenges, have some dummy validation data sets, so everyone can kind of compare against themselves. Also kind of in the developing phase, in the sense that not only on the leaderboard, but I would be very, very interested to know what is the training evolution on a fixed data set, me compared with the first place solution, to see if my tricks are better than their tricks, right? Because then you can say, okay, if everyone used this arc phase trick and everyone did this kind of fine tuning, then what makes the difference is, this sort of learning rate decay tricks and the number of hyperparameters of arc phase and these sort of things. So my suggestion would be just to have like a very dummy validation set open for the participants. So, and probably you will read a lot of threads about internal validation scores and everyone posting there, I got this, I got that. That is also very, very cool and empowers even more, the community and the people that wants to join. So, yeah.
And one question for this slide, when I'm looking at, so have you tried to, like, let's say, have you tried to use 256 as the embedding and then do the PCA? Have you like varied that number yet? Because I guess that since directly training the 640 doesn't work, but is 512 the optimal sort of dimension that you picked?
If you want to answer, Simon, before I leave, but from my side, we didn't test more things than what is written, basically, I think. So,
so if you have to go, thank you very much, Marcus.
Thank you,
so much.
guys.
Merci, Marcos.
It was a pleasure. Hope I can meet you again at CEPR or ICCV. That could be very interesting. I will be down to participate in every challenge. And thank you so much for the organization. Thank you, Maggie, also, Kaggle, the Kaggle team. It's always a pleasure. Bye.
Thank you.
Thank you.
Okay, do you have any additional question?
Pretty much on my side. That's it.
Yeah, my side, I'm done too. Mario?
Also, I have used all my questions, but I like the question that Kaifeng asked also previously. It was like, if there are some other things that you would like to try that you didn't try during the challenge, like if you get some insights on things that you would like to try.
On my side, there is one thing I would like to try, but I can't, is what if I go beyond 64? But I can't, because I can't change the Kaggle server. But so I would, for this wheel, I wanted to ask you, what if you remove completely this constraint and you apply the raw VH output with 1024? Do you do better than the best solution of the challenge? Like, did you try that on your side?
Not
Not with the pre-trained clip model, but it sounds like an interesting experiment.
Yeah, because I guess it's for efficiency, like storage, etc., that you apply this constraint. But like, I'm curious about to know, like, is it really useful in terms of performance?
Yeah, I mean, because ideally one could actually learn clip with 64 dimensions, right? I mean, you could also just do that if we had the resources, etc., etc.
Yes.
That could be like another option, yeah.
And if I may, I've got two questions. So the first one is, what did you learn from this challenge?
So I can start with that. So we definitely were not expecting people to kind of, that clip would be such a high performing baseline. I don't think anyone has done that before in terms of like kind of pre-trained models for this type of image retrieval and deep metric learning, kind of using these image text data sets as pre-training data. And whenever I saw people were using that, I said, oh, yes, it makes total sense. So much better than ImageNet, right?
Yeah, sure.
Because ImageNet is so high-level classes, and text is when you write something, you're probably going to write something more specific, right? So it's not going to be like, oh, this is a photo of a dog. Oh, no, this is a specific type of dog or something like that, or my dog, and I have other picture of my dog, and then that helps provide signal, right? So that was definitely something that at least I was not expecting, and it was a great connection that was made. That is definitely one of the things. Yeah.
Okay.
I think for me, since the pre-trained backbone already performed quite well, if you just randomly select 64 neurons, you already can get 55, I think. So the extra maybe like 13% or 15% are amazing, and especially I think the most the trickiest part is how to really compress the embedding to 64, because that's also the same dimension that we care about internally. And I think those knowledges are very important, because we tried something internally as well, and we know that shrinking the dimension size is not as easy as we expect. So seeing that people try to do the PCA and try to sort of have intermediate dimension and then do the PCA, those are things that are quite inspiring.
Yeah.
And also the model subassembly, I think those are also things that we are internally too.
For me, what I expected was for people to like more try to use some local validation sets, but actually what we've seen also, like top teams didn't use those and basically just optimized the score in the competition, and also like the 6 team tried those but mentioned that like it didn't help too much. So I guess we like I would, if we do some the competition like this in the future, like, it would be really great to have some set of images so that the people can really like see what they can improve on concrete examples that will be more aligned with our distribution. So, but it was very hard without the data.
And my second question is, you have much more powerful model internally than CLIP. Did you try it? Like Basic, Coca, etc.
Short answer is yes. Short answer is yes. Short answer is yes, definitely. We are exploring some internal pre-trained large models. The size probably is slightly bigger than the ones that you are using, and the trained data certainly is more from internal collected data sets. But yes, we are also that's why we are expecting the participants to also follow that direction as well.
Okay. And is it how Google Lens work? Because I'm really amazed by this product.
So we collaborate with like research teams like such as Anders and Kai Feng's, and I wanted to say one more thing, but now I forgot. Oh, that's terrible. About these large models, it's also like that. Interesting that you may, like in the competition, you only see one number, but you may actually optimize for different verticals, and like some of them are easier than others. So so it's also like a bit hard to directly like compare models, but like I guess in the future we should make sure that like the hardest verticals are like of higher even higher importance.
Okay.
Yeah.
Well, I could ask questions forever, but maybe you don't have time anymore. I don't know.
Yeah, maybe we can. We have such a great discussion. Yeah, thanks again, Simon, for being available and presenting. So yeah.
Yeah, you're more than welcome. And it's a pleasure to be involved in this challenge.
Congratulations again. Yeah.
Yes.
Congrats.
And on behalf of Kaggle too, congratulations.
Thank you.
Thanks.
Okay.
Absolutely.